of the same name, which was recently published in Materials and Design. So if you're further interested, go take a look at that. But yeah, so we have basically have a stiff competition going on for decades, where the microstructures, various microstructures, have taken the place as stiffness optimal, isotropic stiffening optimal of this structure by Berger and this one by Gertner, this open wall truss lattice and the closed wall plate lattice, and then these orthotropic stiffness optimal lattices proposed by Sigmund and his team. But we have been missing a part of discussion, which is the buckling strength. So we set out to add to this discussion by a systematic study of these common single-scale microstructures from the literature. So basically, we do homogenization, and then we do linear eigenvalue buckling analysis with the addition of Floquet-Bloch wave theory. So basically, we have this eigenvalue problem, and we have this Floquet-Bloch operation we add to the buckling mode. And the easiest way to describe this, what it does, is by this by a 1D example. So we have this our buckling mode, which is then set to this sine function here, and then we add this Floquet-Bloch operation to the buckling mode. So here, this K is the wave vector describing the periodicity of the buckling mode, and R here describes the periodicity of the unit cell itself. So if we go ahead and put the K vector to be equal to 1, this Floquet-Bloch operation returns to being equal to 1, so there is no real change to the buckling mode itself. So we can see here that the sine wave is unaffected, and we get a periodicity of the buckling mode of 1 unit cell. So this is from one end of the unit cell to the opposite side of the unit cell, so to say. So the black curve here describes the local deformation, while this red curve here is the Floquet-Bloch operation, which describes the global deformation, so to say. So if we set the K, the wave vector, to pi half, now we see that we get some global deformation changes to the unit cell, and we can see that the periodicity of the buckling mode is now 4 unit cells. And if we go to K equal to pi, we see here that once again we have some global deformation, and if we evaluate the Floquet-Bloch operation for K equal to pi, this operation will become -1. So you see here that the value of the buckling mode is a half, and then on the opposite side it's -1/2. So here you get a periodic mode, where for K equal to 0 you get anti-periodic mode, and for K equal to 0 you get a periodic mode. So the problem is then, do we need to sweep from -infinity to infinity to find all the possible boundary conditions? Luckily, we only need to sweep inside the brilliance zone, which is here described by the black box here. So that one spans from -pi to pi. However, due to symmetry in the locus and the geometry here, we can reduce the brilliance zone to what's called the irreducible brilliance zone. So here for the uniaxial case, it looks like this inside the red domain here, and then we can go ahead and evaluate the different wave vectors. So for example, for K equals to 0, 0, 0, we would receive this buckling mode here of this simple cubic truss lattice, which is periodic. And on the other hand here, if we take this R point here, we will get a pi, 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 which then is an anti-symmetric mode. So, and right next to this symmetry point here, there is a pi divided by 20, which yield a global deformation mode, a global shear mode. So the problem now becomes to find the boundary conditions that yields the lowest buckling strength. So we find the boundary conditions that has the lowest buckling strength. And we do that by sweeping the band diagram. So basically we sweep all the edges of this irreducible Brillouin zone, and we put this into the band diagram, and we find the lowest buckling strength. And that turns out to be this global shear mode right next to the symmetry point. So this point, this mode here is actually the critical buckling mode for this structure. So we went ahead and did that for some representative microstructures. Here is the isotropic plate lattice presented by Berger, an orthotropic plate lattice. We have a isotropic plate truss lattice and a orthotropic truss lattice, and then we also evaluated for the hollow versions of these two truss lattices. And then we also went a little bit into the hierarchy of these structures, but I will get back to that later. So we swept the irreducible Brillouin zone, and if we just focus on the isotropic plate lattice and the isotropic truss lattice, we can see here that the band diagram is pretty much flat for these structures, meaning that they're insensitive to the boundary conditions. However, their orthotropic counterparts here, the simple cubic truss lattice and the simple cubic plate lattice, they are sensitive to the modes, to the boundary conditions, but they have overall higher strength than their isotropic counterparts. And then we also see that these hollow versions here actually outperforms their solid counterparts also. So here the highest performance, the highest strength is actually coming out of the hollow truss lattices. So what we then did was we did a study on the volume fraction. So we went from a low volume fraction up to a volume fraction of 0.5, and we did a interpolation scheme, which is usually done in the literature. And so for the Young's modulus, we see here that we have this coefficient A0, which describes the performance in the low volume fraction, and then A1 here describes the performance in the higher volume fraction. And as we did a study on stretch-dominated lattice structures, there is no dependence. There's a linear dependence on the volume fraction. However, for the buckling case, we have the coefficients once again, but we see here there is an exponent to the volume fraction. So if we set the coefficients of the microstructures up in a table, we see here that the plate lattices here for stiffness has a higher coefficient compared to the truss lattices. So they are stiffness superior compared to the truss lattices. However, if we go to the buckling strength, we see here that the exponent, the N0 here on the buckling is higher for the plate lattices, meaning that they have worse performance in the low volume fraction. So the truss lattice here has exponents 2, where that means that they have better performance of buckling strength in the lower volume fraction. And once again here, the hollow versions actually has even lower exponent, so that means they also perform better than their solid counterpart. So now we figure out that the plate lattice is stiffer, but the truss lattices are stronger, so we can't really say which one is the optimal. But here we propose that to find out which lattice structure is actually the optimal one, you need to account for the macro structure. So we went ahead and made this composite beam example, which is basically a beam subjected to equal but opposite end moments, and then this beam is then built of these microstructures. So we set up we can set up the displacement at the midspan, the equation for the stress, and an equation for the mass. So what we want to do here is minimize the mass, but ensure that the beam doesn't fail. So we constrain the problem to have a square cross section, and then the height of the beam is then a free parameter. So we can eliminate the height h of the beam, and then we can set up some constraints on the beam. So here is a displacement constraint on a beam, and a buckling constraint, a microstructural buckling constraint, and a microstructural yield constraint. So the optimal beam will be the one that satisfies both the displacement constraint and the buckling constraint, or the displacement constraint and the yielding constraint, depending on where we operate, if it's yielding or buckling that is the dominating failure mechanism. So we set up a reference beam of a solid epoxy, could be whatever. We chose to do epoxy, and then the displacement of that reference beam is set as the constraint for all the beams. And then the constraints is, of course, the buckling of the specific lattices. And then you could put in some data and figure out which one satisfies the constraint. But it is actually easier to do this in a graphical way. So we can go about it a little bit different. So if you take a look at what's inside the parentheses of this equation here, they only depend on the material properties, and the things outside the parentheses here, they depend on the geometry of the beam. So we can actually plot, we can set up an Ashby multi-objective plot with these material properties as the axes. So we call these material indices. So here M2 is the stiffness index, and M1 is the stress index, so either buckling strength or yield strength. And once again, as the optimal beam is the one that satisfies both the displacement constraint and the buckling constraint, or the displacement constraint and the yield constraint, we can equate the two material indices with each other. So basically we set up an equation where M2 is equal to M1, and we gather all the geometry parameters in this coupling line C, and I'll get back to that in a little bit. So if we go ahead and plot the strength index and the stiffness index on the axis here for this specific beam, we have these exponents, which is specific to this beam in bending problem. And then we can plot the performance of our microstructures here. So here the colors correspond to the colors up here, and the solid ones is the solid plate, the two solid plates, and the two solid trusses, while these dash dotted lines here is the hollow versions. So we can see that we want to have high strength, then we need to be to the right, and we want to have high stiffness, we want to be upside. So the optimal microstructures will be up in this area. So we can see that here that the hollow versions are the one that are performing the best. And here I should mention that these colored markers here indicate the volume fractions of the individual lattices. So we get back to this beam in bending problem. We have our reference epoxy beam here with a length of, we set it to equal to 1, and we have a reference weight saving here, so that will be equal to 1 for the reference case. But want to simplify it a little bit, so we just want to account for the isotropic structures. So the green one will be this solid isotropic structure, and the blue one is the solid isotropic plate lattice. And then we get back to this coupling line here. So this line here couples the geometric constraints on the problem. So whichever microstructure is crossing this beam at the highest point is the optimal one. So that means here that this specific beam problem prefers to have this isotropic truss lattice. So we can see here that we have the reference beam here of solid epoxy, and then this point here corresponds to having the beam built of these isotropic truss lattices with a volume fraction of 0.02, and we'll get a reference or a weight saving of 2.9. So just to reiterate, this coupling line here determines the geometry of the beam, and whichever beam or lattice crosses this line at the highest has the highest weight saving potential. So for this case, the optimal lattice would be the isotropic truss lattice. But if we go ahead and take half of the beam length, then we can see that the two different lattices are approximately hitting it at the same time. So we can see that if we halve the length of the beam, we actually get a weight saving of 2.0 and 2.1 for the respective lattices. And once again, if we do a quarter length of the beam, we can see that the beam now prefers to have this isotropic plate lattice instead. So with this Ashby method here, it's easy to account for the geometry of the beam, and we can graphically see which one is the best. So here we propose that to see which microstructure is actually the optimal one, we need to look at the macrostructure because it's depending on that. So now I told you we would get into the hierarchy of these microstructures, which we have also been looking into. So we here take Lake's formulation of microstructures here, which is that the microstructure is self-similar, meaning that it has the same shape and volume fraction at each level. And here we can see that we have the same A0 determining the performance of the stiffness, but now we have added this n exponent here, which determines the level of the hierarchy. So for a first order, that will be equal to 1, and you will get the same normal interpolation function. However, if we take it to be second order, we would actually have an exponent of 2, meaning that you would actually lose stiffness because A0 is always below 1 and sometimes significantly below 1, so you would lose a lot of stiffness. However, for the buckling strength, it's a little bit more complicated, but basically it's the same. But at this point here, as we have an exponent which is non-zero, we would get a lower slope, meaning a better performance in the low volume fraction. So there is some limiting volume fraction where the performance is actually better. So if we take a look at it graphically, we can see here for the isotropic truss lattice, we have the first order, the second order, third order, where we lose stiffness each time we go up in order of magnitude of hierarchy. However, for the buckling strength, we have the solid one here, which has an exponent of 2. But if we go to a second order hierarchical lattice, we actually see at some point we start to get better performance of the lattice structure. And then if you go to third, we get even better at some point. After some point, some limiting volume fraction, you would get better performance. So actually, if you go to the infinite limit of hierarchical orders, you would get a dependence that is linear on the volume fraction, which is desirable. But at that point, you would have lost all your stiffness, so it wouldn't have mattered anyway. But yes, so if we then account for this hierarchy in the Ashby plot, we can actually see here that as this has an exponent of 3, it actually has a great benefit from going to a hierarchical version of it. So even though it doesn't matter now if it's full length, half length, or full length, the best performing microstructure is actually the second order version of that isotropic plate lattice. So if you're able to build a beam with volume fraction 0.01 and then make it hierarchical, then you could actually have a weight saving of 5 approximately. But I guess we are a few years away from that still. And then a little teaser on some of the current work that we're working on. Feng-Wen Wang and Yichang Wang and Ole Sigmund and I, we have been working on directional properties of some of these lattices. So here I have a little teaser on the directional properties. So we see here we have the isotropic stiffness surfaces of these structures. But then if we go to the yield strength, we see here that this one is close to being isotropic, meaning that it has pretty much the same yield strength in all directions. But the yield strength of the truss lattice is way more anisotropic. But if we account for the buckling strength surface also, we can see that here it is way more anisotropic compared to its yield strength surface. But for the truss version here, it looks pretty similar, and that makes has a lot of importance, as now the dominating failure mechanism can be determined purely by the base material and the volume fraction, whereas for the plate lattice here, it's also highly dependent on the load direction. So we are getting ready to publish a paper on this, and so if you're more interested in that, be on the lookout for that. So thank you for your attention.